be introducing our education research panel. As Michelle said, one of the aspects of the field that we wanted to dig into to frame what we're doing in this meeting today is that there's quite a bit of related work in different fields that has been going on for quite a few years that we can draw on communally as we're beginning to work together under this moniker. And so we asked a set of colleagues who can provide perspectives on that in this panel on the education research related literature that can be drawn upon. So our panelists are Andee Rubin, right here. She's a senior scientist at TERC in Cambridge, Massachusetts. She's conducted a wide range of work in schools and museums related to data literacy and statistical reasoning. I'm deliberately giving brief introductions to these people because they are so venerable it would take forever to be complete. Dani Ben-Zvi is a professor, Dani over here, in the Faculty of Education at the University of Haifa in Israel. His work focuses on statistics education and educational technology. Rogers Hall is a professor in the Department of Teaching and Learning at Peabody College, Vanderbilt University. He studies mathematical activity and representational practices in school and work settings. Our discussant, Janet Kolodner, where's Janet? Is Chief Learning Scientist at Concord Consortium and Regents Professor Emerita in Computing and Cognitive Science at the Georgia Institute of Technology. In addition to her own R&D, Janet was founding editor of the Journal of the Learning Sciences and the lead program officer for the initiation of the National Science Foundation's cyber learning program, with which many of us in this room have been involved with, and was a meeting at the annual meeting for cyber learning generated this event that we're at right now. So with that, it's my pleasure to introduce Andee Rubin. We're going to go in the order that's listed on your agenda. Andee, then Rogers. No. Andee, then Dani, then Rogers.
Okay. And we have 20 minutes, is that right?
Yeah, I'll give you a prompt with about 5 minutes to go.
Okay.
Andee, do you want us to take the lights down a little bit?
That's probably a good idea. Yeah. I think many of you understand the problem of if I put on my glasses, I can see this, and then otherwise I have to look at that. So I might be doing on and off. So this is really a pleasure to be helping to kick off this meeting, and I'm really excited about this expanding community that's thinking about data science. My title slide kind of gives you an idea of the way I think about this. I feel like I've been around, well, I have been around for decades doing this kind of work, and it's gotten called all kinds of things. Data analysis, statistics, statistical reasoning, data literacy, and it seems like things come and go, and now we're talking about data science. And so my questions are, so what's new, but what's still the same? So what have we learned in the past? My wife reminded me it's been 30 years. I was saying 20. She said, no, actually, you've been doing this for 30 years. What do we know? But what do we still not know? And maybe what are some new things that we don't know because of some changes in the environment? So I decided I would just do some personal history. And what I'm going to try to do is, from the projects that I've selected, is to try to extract a lesson from each of them so that I can start to answer that question of what do we know, and then see which things we still don't know. And I have some lovely artifacts here that I think qualify as, like classic cars. So the first thing I want to talk about is used numbers. How many people have heard of used numbers? Yay, all right. So the publication date on this is 1989, and this is a complete K-5 curriculum focusing on data. It's actually 1 unit per grade level. It is a lot of what investigations in numbers, data, and space, which you certainly have heard of, came from this. And this was my introduction to thinking about data. And I was looking at this, and realized that there is a beautiful statement there, which I have in red, and it kind of vibrates a little against the blue, so I apologize for that. But I think the big lesson from this is that elementary school is really the time when students should start working with data, and I'm very unhappy with the current core curriculum that doesn't have any data in it until 6th grade, which just seems wrong to me. And I love this, now I'm really gonna have trouble. All right, whoops. We introduce students to good literature in their early years. We do not reserve great literature until they are older. On the contrary, we encourage them to read it, or we read it to them. Similarly, we can give young students experience with real mathematical processing rather than saving the good mathematics for later. Through collecting and analyzing real data, students encounter the uncertainty and intrigue of real mathematics. I think that is just a beautiful statement. It was written by Susan Jo Russell, and I think, oh, thank you, okay. So we learned that, and I think this is as true as ever, that students should start working with data in elementary school. It's very natural for them to start with data about themselves. How many teeth have you lost is a very common thing, which I noticed Dani's going to talk about too. And then students are also very interested and motivated by collecting data with which they can make arguments about changes to their environment. So the big thing in used numbers was collecting data about playground injuries and making recommendations based on that data about changes to the playground. I think those are things that are as true today as they ever have been. How many people remember Statistics Workshop? Not quite as many. Tim does. So this is software that I designed almost 30 years ago. And the interesting thing about this software were these two aspects. One is called stretchy histograms, and the other is called shifty lines. And the idea of these was that rather than just creating representations of data, that you could change the representations themselves with direct manipulation, which was new at the time, and actually see how the summary statistics or the aggregate values change. So with the stretchy histogram, rather than just putting data into a histogram, you could move the bars around, and you can see on the bottom there's an indication of the median, of the mean, and of the quartiles. So this is a way for students to interact with data in a way that helps them get an idea of aggregate values in particular, which are hard for students to understand. Shifty lines was a little different. It was about understanding what a line of best fit looks like, and as you shifted that line around, the unexplained, actually the sum of the squares of the data away from that line are shown in that thermometer. And the minimum value is the dark gray, and the extra scatter around the line is the light gray. So again, a way for students to understand these things that are very equation driven often, but in a direct manipulation and visual way. I think what we learned from that, which is still true, is that interactive visual representation supports students' intuitions about the relationship between data and aggregate values in particular, in a way that non-interactive representations may not do. This was, I couldn't get a picture of this because it doesn't run anymore, so that's why that's the classic application icon. But we also developed a way of seeing sampling that had multiple views of a sampling situation. So it had a population, it had individual samples, and from each of those samples you could see what the aggregate value was, and then it had the sampling distribution. So it had all of the perspectives on sampling at one time, and you could go back and forth between them. So you could select a particular aggregate value, double click on it, and go back to the sample that generated it. So again, something that we learned in developing and watching students use this software that is certainly true today is that the whole idea of sampling and sampling distributions is very difficult for students because it requires this shift in attention from a population to a sample and then to some value computed on that sample. But none of that really matters. It's really the distribution of the sampling statistics. It's a very complicated and counterintuitive landscape. And this piece of software, I think, helped. This is still a really difficult topic for students. So then in the early 2000s, I did some work with Jim Hammerman, who's right here, and with Cliff Knold and Bill Finzer, who is not here, but Tim Erickson is here as, as our Bill Finzer. And we did work with middle and high school teachers, and you gave them both Tinkerplots and Fathom. And I am purposely not saying a lot about all of these pieces of software because I would never get through everything. And we tried to see how they used the software to get some idea about how relatively novice statistical thinkers use software and what we can see about their statistical reasoning through their use of the software. And this is an image from a paper that Jim and I wrote. And what we see here, it's a scatter plot, and we asked teachers, so what do you see here? And they wanted to make deterministic statements. And this is a very general trend, but they looked at this and they said, oh look, there's nothing up there. So the main lesson that they took from this picture, which has a lot of variability in it, is that if you're above this line and to the right of that line, it doesn't happen. So that the probability is 0 over there, as opposed to the much more complicated question of how do you describe all that other stuff. So again, I think this is something that is still an issue for novice statistical thinkers and even growing statistical thinkers. Probabilistic thinking is really hard. It's much easier to make deterministic statements that are like, that never happens or that always happens. So that's something that we are always kind of pushing up against. In 2005, I wrote something called Math That Matters, trying really hard to make the argument that actually students might be better off studying statistical reasoning than calculus for a great many students in terms of utility in later life, in terms of actually enjoying the math, feeling like it was useful, feeling like it was related to them. So I wrote what I thought was an absolutely persuasive argument that we should replace the algebra calculus track with data literacy. You can see how much traction that got. Although I have seen other people making that argument recently, but it's still not changing the curriculum. So the lesson that I learned from this, it's very difficult to shift curriculum priorities, even in the face of well-reasoned and persuasive arguments. Now, I think a lot of what we'll be talking about today really is political also. We are all convinced of the importance of data, but there are powers that be that may not be. And so I think that we need to keep that political perspective in mind as well. Okay, then I want to give a big shout out to the SRTL community. Dani will talk about it a little bit, maybe not. But SRTL is Statistical Reasoning Teaching and Literacy. I think it's research, but it's not. But it's a community that's been doing work on statistics education for 20 years. We have our 10th meeting coming up next year. It's very small meetings, about like this. They're a week long. Everybody spends every minute of every day together. And a lot of intellectual work gets done. And one of the things that came out of that whole community and their meetings is an idea called informal statistical inference, which I think Dani will talk about a little bit more. Oh, I'm going to talk about it, okay. But a lot of people have been talking about the fact that the structure of formal statistical inference is difficult. There are both the probabilistic aspects of it and just the whole kind of reverse, think as if something is true and then it's not, and so therefore you've decided that what you started out with is true. So we started looking at students, younger students, and what is it that they can experience about statistical inference, which is, I think, a big part of the power of statistics, to be able to say something about what might happen in the future or what might happen in a larger group based on what you know about a smaller group or a sample. And Katie Mocker, who is at the University of Queensland in Brisbane, and I wrote a paper that says, here's a framework for thinking about informal statistical inference. And it's gotten a lot of purchase in the stat ed community, and I think it's actually really useful. And we said there are three things that characterize informal statistical inference. One is going beyond the data at hand. So you've got some data and you're making some kind of statement that goes beyond what you just have in front of you. Using some kind of probabilistic language. So you can never make a definite statement if you just have partial information. So recognizing and articulating that there is some probability around this, that there's a chance something is more likely than something else, something is very likely, something is not very likely. But also using the data as evidence. So not just making statements that are based on a single event or a single piece of data, but really understanding the role of data as evidence and then going beyond it. I will bring up in a few minutes, I'm wondering about the role of inference these days in the era of big data, and I think that's one of the interesting things that we might want to be thinking about at this meeting. But I still think this idea that inference can be done without all of the hypothesis testing mechanism, and that there are important understandings about inference that can be accessible to younger students, I think is still a really important piece of learning about statistical reasoning. And my current work, I'm working with Joe Polman without an E, and our grant is STEM literacy through infographics called FLY. We're right in the middle of it. And this is a project in which we're working with teachers who are then working with their students to create infographics around science topics, generally of their own choice, using data that they find on the web. So in general, they're not collecting their own data, they're finding data. And so a big part of what they have to do is figure out how to move data from one place and one structure into another piece of software. So we have an infographic tool that they're using called Venngage, and then they find data on the web, and it's not in quite the right structure. So a lot of what we're realizing is that an important skill these days, when data are out there on the web, is understanding enough about the structure of data that you can figure out how to move it into another tool. And we just had a teacher institute a couple weeks ago, and I realized that an important thing that I could contribute to the teachers was focusing on the idea of a case, which to me is like, I've been thinking about cases forever, but that was not a concept that those teachers necessarily had in mind. And the distinction between a case and summary data was actually, I think, an eye-opener for some of the teachers. 5? Okay, good. And the cases could be different things. They can be people, they can be countries, they can be years. And if one piece of software is expecting data organized around countries and another is expecting data organized around years, what do you do? So I think this is a newer skill because all those pieces of software that manipulate data are out there. So I think it's a really important emerging kind of understanding of data. So here we are today, and what is new? And I think the big thing that's new that we have to think about its impact on all of these things that I think we really do understand is technology and the ubiquity of data. That really is something that's changing the landscape. And I had a very interesting multi-way conversation with Rogers and Jen, who I think is here. Yeah. And Rob Gould, who some of us know, who is a statistics educator at UCLA, about what's the role of inference when you have a population? So is inference passé, or is there just a new way of thinking about inference? And I've copied a few things here from an email that Rob sent to the three of us, which I thought was just brilliant and needs more thought. So he did say population data sets provide an opportunity for rich storytelling without the hurdles of mathematical inference. So that's an important thing to know, and that storytelling still has an enormous number of skills associated with it. But he said, but then there's this thing called causal inference. So even with a population such as the census, we might wonder why there are more people living in cities this year than last year. Causal inference is hard, and there's a growing body of literature devoted to unraveling its mysteries. And I actually don't know that literature, but that would be really interesting literature, I think, for this group to look at. But more subtle is when inferences are made not to a new population, but to the future. Because as Rob's email went on, we take random samples of a population. We don't take random samples of the future. That doesn't make any sense. So how do we make inferences to the future? And that's really about building models and identifying the assumptions that went into building the models that allow us to make inferences to the future. But that's a whole new thing in some ways, different from the old style statistical inference. So I think that's one implication of what's new. Another is that because data are out there and we get them kind of prepackaged, understanding the measurement conditions and assumptions is extremely important. More so than when mostly we collected our own data or we got data from down the street. But it's out there, who knows how it was collected. And often those underlying assumptions make an enormous difference in terms of the meaning that we make from the data. And also, therefore, because of the ubiquity of data, cleaning data is actually a big piece of what people have to do. But a NSF program officer recently said, and I will not tell you who this is, oh, cleaning data is really 95%. We know how to do the analysis. I would say he's off. maybe he's got it reversed. But so I do think cleaning data is important, but people who say that's what data science is and we know how to do the rest, I just think, no, not true. So we need to guard against that. And what do we still not know? Actually, this is just the beginning of a list because there are many things we don't know. But I still think we need to think about how to reestablish data analysis as a critical skill and where to fit it in the curriculum. Because people say, we've got to do more data science, and then people say, well, what are we going to take out of the curriculum? And at the same time, people are saying we have to do computational reasoning, and what are we going to take out of the curriculum? So I think that's a big question, just where does it fit? And this is an issue that I've felt is interesting for a long time also, is how to foster the appropriate mix of skepticism and belief in data in kids, adults, policymakers, anybody, because often we skew towards that, look at all these ways you can lie with data, and then people start to feel that, well, data doesn't do you any good. On the other hand, you certainly don't want to just assume that anything that's numerical is true. So I think there's a really interesting question of how we foster an appropriate attitude toward data. And I thought I had one more thing to add that I just thought as we were starting this meeting this morning, which is how do we look at the new landscape of data science and see what new skills might be important and still hang on to the understanding of those old skills that we've been working on for all these years, and how do we put those together, honoring both of them, and hopefully coming to a whole that's larger than the sum of its parts. That's exactly time. All right. Thank you.